In section 4.7, we're going to take a look at optimization problems. These are a series of problems that kind of highlight and showcase one of the powerful uses we get out of the calculus concepts we've already discovered thus far in the class. Let's take a look at example 1. They say that a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with the maximum volume? Okay. Let's go ahead and solve this one together. And one of the things that you're going to notice, in addition to the calculus concepts we're going to use, we want to employ a lot of the same concepts we would have done previously in just general mathematics courses. Let's see if we can just draw a picture here. So first of all, one of the things we know is that it's going to be a box that's going to have a square base. And this is a very, very rough sketch. And make notice of the thing that they say it's going to be an open box. So this box is not going to have a top on it. So whatever the length and the width are, because it's a square base, those are going to be the same. One of the things that I don't know is how tall the box is going to be. So let's introduce a second variable. Let's call that y. What we want to do is we want to maximize the volume. Okay? We know volume is equal to length times width times height for a box. And in this case, the volume would be equal to x times y, which is going to be x squared y. Obviously, if there's no restrictions, you can make a box with longer and longer and longer sides, and the box will have a larger and larger and larger volume. However, we're constrained to the following scenario. So our constraint equation here is that the total surface area must be 108 square inches. So the surface area must be 108. If we look at the box in terms of the surface area, this box, because it's open at the top, will only have 5 sides to it. You'll have the left side, the right side, the front face, the back face, and then we'll also have the bottom of the box. If I focus for a moment on the bottom of the box, okay, this surface area of the bottom is a rectangle, it's a square, with sides x and x. So the surface area will include that side, which has area x squared. If you look at the other faces then, let's take a look at maybe one of the side faces. Okay. You can very quickly look at the diagram and look at the picture of the box and realize that the 4 remaining faces will all have an area of x times y, right? This would be this side times width. If you look at the front face, it would have dimensions x by y. So the area of the 4 resulting faces, each face would have an area of xy, and there's 4 of them. So this would give us an equation for the surface area. 108 is equal to x squared plus 4xy, and this is referred to as our constraint equation. In order to maximize the volume, what we want to do is we want to analyze the volume function, but we don't want it to be a function of 2 variables, which it would be right now. We have the volume expressed in terms of the variables x and y. Ideally, we'd want to write the volume as a function of either x or y, and in this case, we can do v as a function of x by doing the following. If I come down to my constraint equation, I can solve the constraint equation for y. And I would do so by doing the following. Just subtract x squared from both sides. We would have 108 minus x squared equals 4xy. And then divide everything by 4x. We would see that y is equal to 108 minus x squared divided by 4x. And now what we can do is we can use this expression for y to substitute it into our objective function. So we can write volume as just a function of x. V as a function of x is going to be equal to, it's x squared times y, where y is 108 minus x squared, divided by 4x. Let's go ahead and simplify this. We can cancel an x from the denominator with one of our x's out in front. So this is going to be x times 108 minus x squared all over 4. We can go ahead and simplify this a little bit. Let's distribute the x in. We would have 108x minus x cubed over 4. And because this is just a constant denominator, let's split apart the terms because it'll make the differentiation part easier. If we were to do 108 divided by 4, that should give us 27x minus, and this is going to be a 1/4 x cubed. If we wanted to find a maximum or a minimum for this function, we should start by finding the critical numbers. I'm going to take the derivative, set it equal to 0. V prime of x would be equal to, and I believe above, I forgot to put my x on that 27. So 27x minus 1/4 x cubed. The derivative is going to be 27 minus, bring the power 3 down. 1/4 times 3 is 3/4. Reduce the power by 1, we get x squared. We can solve for where this is equal to 0. So when is 0 equal to 27 minus 3/4 x squared? Well, we can add 3/4 x squared to both sides. The next step is you would want to divide by 3/4, which would be equivalent to multiplying both sides by 4/3. That'll give us x squared equals 27 times 4/3. It's going to be 36. And then we can solve for x by taking the square root of both sides. Whenever you take a square root of a real number, we should get two solutions, plus and minus. However, because x physically represents the side of a box, we need the positive root. So we would get a value of x equals 2 to 6. Now we don't know whether or not that value produces a max, min, or perhaps neither. So what we would want to do is check the second derivative test, or even the first derivative test, to see whether we yield a max or a minimum at that value. Also, in terms of our critical numbers, we should also look perhaps for where v prime of x would be undefined, but our derivative in this case was a polynomial, and those are defined everywhere. So you won't find any critical numbers of the type v prime undefined. To check to see whether this is a maximum or a minimum, let's go ahead and do the second derivative test on this one. If I calculate v double prime of x, v double prime of x is going to be equal to, here's my first derivative. If I do the derivative of this function, the derivative of 27 is 0. I would bring the power 2 down, so I would get negative 3/2, because negative 3/4 times 2 is negative 3/2. Reduce the power by 1, so it's x to the first. V double prime, so the second derivative evaluated our critical point, would give us negative 3/2 times 6. And negative 3/2 times 6 would be negative 9, which is less than 0. So if you recall from the second derivative test, what happens when the derivative is negative at a critical point? Well, that does produce a maximum. So we have just shown that the maximum will occur when the value for x is 6. Now let's go back and make sure we're answering the entire question. They say what dimensions of the box will produce the maximum volume. So if you go back and look at our box, we have found the lengths of the sides of the bases. So we know that for our box, it's going to be 6, and this is what, inches by 6 inches. But we also need to say what the height would be. And we can do that by going back to wherever we defined y in terms of x. I've erased it, but if you go back to our equation, when we solved this equation for y, the constraint equation, we said that y was equal to 100 minus x squared divided by 4x. So if we plug in 6, this is going to be 108 minus 6 squared divided by 4 times 6. We'd want to go ahead, plug that into a calculator, work that out. And we should get 3. So that is the answer. If we have a square box and we want to make it with the maximum possible volume, and we're constrained to only using 108 square inches for the surface area, then the dimensions of the box that we would want to use would be a 6 inch by 6 inch by 3 inch box. Let's kind of go back through and recap exactly the steps that we took in this problem, because these are going to be essentially the same steps you will take whenever you're doing one of these optimization style problems. Okay. The first thing you want to do is kind of read the problem through, take inventory of what you have. If it's something that's kind of geometrical in nature where you're able to draw a picture, that would be kind of step 1, draw a picture. The second step is you want to write down the primary focus of what you're looking for. So there will be what we call an objective function. That's the function that you're either hoping to find the maximum value of or the minimum value of. So write down your objective function, and then in addition to that maximum function, that objective function, we oftentimes are going to have what's called a constraint equation. Again, if there was no constraints on this problem, then you could just make the box bigger and bigger and bigger, and the corresponding volumes would get larger and larger and larger for our maximum. Here, though, because we're constrained, we're limited to only having a total surface area of 108, that puts some restrictions on the dimensions of the box that we're allowed to use. Okay, that's step 3. The fourth step is you want to use your constraint equation, solve it for one of the variables, so that you're able to rewrite your objective function as a function of a single variable. In this case, we chose to do v as a function of x because it was a little slightly easier. From there, you would then want to go ahead and try to find the maximum or minimum by using the standard calculus we did earlier in the chapter. Find your derivative, do the critical numbers, and then through either the first derivative test or the second derivative test, find the critical numbers and test them to see whether they are a max or a min. And then at the very end, just make sure you're answering the full question that's asked. Here, we were only asked for the dimensions of the box that would produce the maximum volume. Sometimes they might actually ask, what is that maximum volume? In which case, you could simply plug the x and the y value into the v function, or you could even just take this single value x equals to 6 and plug it into our v of x function.